Hi everyone, in this video we are going to calculate the work done. There's a hair on my iPad. We are going to calculate the work done on an object and start seeing how this change in energy can look depending on that work done and on the total work that's done on our object. This right here is our total work and energy theorem. We will be basically living this all throughout chapter 6, and we will be referring back to it several times throughout the semester because it is one of the most, if not the most important idea in physics, that our total energy is conserved, is one way to phrase this. So let's look at this problem. Again, all of these problems and all these slides are posted on Blackboard, so you can check out those problems and work them on your own if you want, or work them alongside me as I work them. But as a quick, simple example, here we've got a person pulling a suitcase. We know the force that they pull, 25 newtons. We know the angle above the horizontal that it's directed, 30 degrees. And we know the distance that they move. We want to find the work done by that pulling force, F. So our work, I'm just going to zoom in to write a little neater. Our work is our force multiplied by our distance multiplied by the cosine of the angle between the force and the displacement. Our force was given as 25 newtons. I'm going to multiply that by our distance, 40 meters, and multiply that by the cosine of the angle between the two, 30 degrees. When I calculate that out, I get 866 joules. Note how that is a positive value. When I take 25, 40, and cosine of an angle less than 90 degrees, cosine of that angle smaller than 90 gives me a positive. That positive sign for our work means that energy was added into my system. Added, let's say, to my system. Added to the system. Energy was put into my system. How much energy? Exactly this much, 866 joules. Now as I pull, I know that the velocity of my object, my system of interest, is going to increase, right? A force is going to lead to an acceleration, so I'm going to be going faster and faster and faster. So just like in the last video, we described that windsurfer moving. As the speed increases, we're going to say that's a bigger energy as the speed gets bigger. We'll classify specifically what kind of energy that is in the next video. But that's how much work I've done on this object. Let's think about another example. Here we've got a woman lifting a box. We know the weight of the box, that's 40 newtons down. And we're going to pick the box up off the floor and put it 1.5 meters higher on a shelf. So the before is the solid picture here, and the after is sort of this grayed out picture, right? We move the box up onto that shelf. One thing we are going to assume is that we are slowly lifting the box. That means that our acceleration is going to be 0. That means if we were to draw the free body diagram for this, just like we have here, the weight force is 40 newtons down. That means the force that we apply has got to be 40 newtons up. So to calculate the work done by the woman on the box, well, we'll say that this is the work done by the woman, W sub W. That's the force of the woman on the box multiplied by the distance multiplied by the cosine of the angle through which it moves. So she's got to push with a force equal to 40 newtons. She moves that 1.5 meters. And then I'm going to be very explicit and say cosine, of 0 degrees. And the cosine of 0 degrees is 1. So 40 multiplied by 1.5, that's going to give me plus 60 joules of energy that I've put into my system, right? The work done was 60 joules. Now part B asks for the work done by the Earth acting on the box. So the work done by the Earth, well, that's going to be the force of gravity. That's the force of the Earth pushing on the box, or rather pulling on the box down. Multiplied by the displacement, multiplied by the cosine of the angle between the two. And now we just have to be careful because my weight was 40 newtons. My distance is 1.5 meters. And then the cosine of the angle between my displacement and this particular force, the weight force, is 180 degrees. If we look at our free body diagram, right, I am moving up. That is my displacement D. So I am moving up. My weight is down. The angle between those is a full 180 degrees. That gives me negative 60 joules, the work done by Earth. So the woman added 60 joules of work into the system, 60 joules worth of energy. The Earth pulled 60 joules of energy out of the system because its force was against the displacement. That means the total work done on that box was 0. Now what we said in one of the very first slides we showed in this video was that the work is equal to the change in energy, I'm trying to adjust it a little bit. Work is equal to the change in energy of my system. For a single object system, if I just take this box as my system, the only kind of energy that I can have is the energy of motion. We'll see when we define potential energy, something called potential energy, that's an interaction energy. And I need to have more than one object to interact. So if you've ever seen potential energy, you might be looking at this problem and saying, hey, that's not how this problem is solved. It's because of the specific way that we're analyzing this problem. We will revisit this problem later after we define potential energy, and you'll be able to see that connection. So there's two quick examples of calculating work using our formula: force times distance times cosine of the angle between the two.